Now joining us, DARPA Microsystems Technology Office Director, Dr. Mark Rosker, and Deputy Director, Dr. Dev Palmer.
We will be talking to you over the next few minutes about working with DARPA and in particular working with MTO. We think of this as MTO 101. So we want to tell you about ourselves, what our mission is, how we work with some of the other offices, and ultimately we would like to describe in some detail some of the ways in which we encourage you to work with us and with our program managers. Most of this session, I believe, I hope, will be interactive, question and answer, but I'll start with a brief overview that gives you a flavor of some of the topics that I just discussed. So let me begin with DARPA. Many of you are very familiar with DARPA, but for anyone who is not, the history of DARPA invariably starts with Sputnik, because Sputnik is the moment in history that was the genesis of DARPA as an organization. As you know, Sputnik was a satellite launched by a foreign power, and that moment was a moment of technological surprise. The nation did not anticipate that was likely to happen. As a result, one of the many results of Sputnik, DARPA was established to guard against technological surprise, and that was and remains our mission today. Now, the way in which we are organized is in 6 different technical offices. They range on this chart from the Biological Technologies Office and the Defense Sciences Offices. These are more technology offices focused on early research. On the right-hand side of the slide, you see the Strategic Technology Office and the Tactical Technology Office, which are more about developing systems and platforms, so large implementations of technology. We live in the middle with our partners, the Information Innovation Office, which is more focused on software and cyber sciences. We are interested in hardware, and we're interested in a number of topics that we'll get to in a few minutes. So we depend on the technical offices, the technology offices for early foundational research, and we also depend on STO and TTO, the systems offices for transition. And that puts us in a position to be coupled to the entire organization. Very briefly, this is a second slide. This is a org chart which gives you some of the names of the office directors and deputy directors in the various offices, and a little bit more detail about some of the specific areas that each office is interested in. Now, the unique thing about DARPA, and the thing that really separates it from other organizations, is the way in which we do business. And specifically, the fact that we have chosen to have a structure in which the people, the program managers, and the directors have limited tenure. You come to DARPA for a brief period of time. You explore an area that you are particularly excited about, and then you leave and are replaced by someone else who has new ideas and different ideas. And this makes it a very dynamic organization. In terms of processes, all processes really have to be very fast by virtue of the fact that there's such large turnover in the organization. And from the standpoint of culture, that derives a very risk-tolerant view. So the kinds of programs and topics that we are interested in are generally quite exciting and hopefully lead to high payoff technologies when they work. It's probably worth a moment to say that because of the high turnover, we are always interested in looking for program managers. So if you are interested in public service and think you would be interested in joining us, please let us know. We're very much interested in that. So the acting director, Peter Heilmeier, uses this slide when he is describing the organization. Generally, lots of interesting numbers at the top, the number of program managers and the size of our budget and so forth. You find that there are actually very few program managers at DARPA. We're a very small organization. From the standpoint of the technologies we're interested, he groups them into 4 different areas: defending the homeland, deterring and prevailing against high-end adversaries, stabilization, and at the bottom, something called foundational research. Much of what MTO does can be found in the bottom area. You can see ERI called out as a specific example on this slide. But we have interest in MTO across the entire surface of this chart. And the one that I would call out in particular of interest is right in the center, control of the EW spectrum. All right. So having said that very briefly, let's get to MTO and let's talk for a moment about the Microsystems Technology Office. So it's always good to begin with our mission. What is MTO about? And this slide says very clearly that our mission is really associated with delivering the technologies that enable higher performance and intelligence in specific areas of interest, C4ISR, EW, and directed energy. And I'd like to say that the message at the very bottom of the screen is a really critical one. And that is that the reason why MTO exists, the reason why it was founded and why it's still here almost 30 years later, is because if you are interested in building systems like this for national defense, the availability, the effectiveness of these systems is largely dependent on the microsystems, the microelectronics, the photonics, the MEMS, the microsystems that are contained at the leading edge of these systems. So it's our job to ensure that we have an advantage over our adversaries in all of these areas. That's our goal. That's what we're trying to do in MTO. And the way in which we try and do it is through 4 thrusts. And we're going to talk a little bit about these thrusts over the next few minutes. So I'll explain them in more detail. But very, very briefly, what these are number one, localized processing, enabling microsystems to be more intelligent. And number 2, electromagnetic spectrum dominance. So the front-end technologies that allow systems to see better and to actuate better than existing than adversary systems. So those are component technologies. The third area is the integration of those component technologies into microsystems. And it's not just the integration themselves, but also their design and their security, which is part of that. And finally, the last area, which as we'll get to, is combining all of those elements, including the integration, into functional microsystems to deliver specific capabilities. So let's go through these one at a time. And some of these, as we'll see, are ERI topics, and some are non-ERI topics. So many of these themes will be very familiar. The ERI ones will be very familiar from what you've already heard over the last couple of days. The first one is embedded microsystems intelligence and localized processing. There are 3 sub-themes associated with that. Let's talk about those. The first one is increasing information processing density and efficiency. And what this really speaks to is having the ability to process signals, to process information with less energy. And you may want to do this for either of a couple of reasons. Either it's because you're interested in processing information at a leading edge, and so the amount of power, for example, that you have available to you is very limited, so you want to process a lot of information maybe with less than a watt. Or perhaps you're interested for other applications in very large computing, but you're limited by the total massive amount of computational energy required to do what you need to do, like in a data center. The second area is making decisions at the edge faster. And what this really is about is one step above what I talked about a second ago. It's not signal processing anymore. What you're really talking about now is making decisions. So as you might expect, this is more associated with artificial intelligence and trying to make better decisions and make it more quickly than you were able to in the past or that your adversaries can do. And the third area is, I like to say, a problem of our own making. It's a problem born of our own success. It's reducing the glut of digitized sensor data. So we live in a world now in which tremendous amounts of information can be digitized, and they can be digitized locally. They can be digitized at a sensor. I'm showing an example here on the right of something that can produce a tremendous number of bits from just a single sensor more bits than can easily be processed by a centralized processing unit. So how do we reduce that amount of information down to the essential parts that we care about? And so that's the third of the sub-thrusts. The second area that I'm going to talk about is next-generation front-end technologies for electromagnetic spectrum dominance. And this, I like to say, is really the traditional area that MTO has been engaged in since its creation, making front-end elements that have exceptional capabilities. Sometimes those capabilities are linearity, power. Sometimes those capabilities are bandwidth. But things that are above and beyond what can be found in commercial off-the-shelf electronics. So some of the three sub-thrusts that this include begin with reducing the size, weight, and power, the SWaP-C, and cost, the SWaP-C of front-end components. Really, this is talking about making things that are large, much, much smaller. Ultimately, we would like to make things like the LiDAR system, the big bulky LiDAR system, which is shown on the left, and is found in automotive LiDAR, for example, autonomous vehicles, much, much smaller, chip scale, if possible. The second area is increasing the tactical range of systems. And from the standpoint of the front end, this really comes down to two things, transmit and receive. So on transmit, can you transmit more power? And on receive, can you detect more in a superior way? Can you have what is often called lower noise figure? So better transmitters and receivers. And on the right-hand side, we have a set of problems that is emerging having to do with robust operation in congested spectrum. This chart shows a spectrum allocation that the United States uses. It's familiar to many of us. It is how, for a generation, multiple generations, we have divided up the electromagnetic spectrum for specific purposes. That's changing, and it's changing very radically. So now we have a world in which we are using spectrum in a much more flexible way, in a much more dynamic way. That presents all sorts of challenges and opportunities. Third area is microsystems integration. Now, integration, as I mentioned before, usually is thought and associated with the processes by which one interconnects and builds systems on a chip or builds systems generally. But here we've expanded the definition to include things beyond that, specifically trying to think about design and security. So really three problems, and they kind of break out into the three areas that I just mentioned. First, overcoming the inherent throughput limits of two-dimensional electronics. Electronics, as we've already talked about at the summit, electronics has for years been confined to two-dimensional surfaces to die. We're moving into the 3D world in which electronics is inherently a three-dimensional thing. And the reason why we're doing this, and we believe it has to be done, is limited by throughput. It's limited by the number of interconnects and the total amount of information that can be passed through those interconnects. So by going to 3D, we have a topology which supports a higher degree of performance. The second thing is another familiar problem at the ERI Summit, and that is the skyrocketing costs of electronics design. So as the number of transistors has exploded, gone from small numbers, thousands, even tens early on in Moore's Law, to now billions, many billions, the cost of designing circuits has become prohibitive for the Department of Defense and for much of industry as well, except for the very highest number of elements type manufacture. So how do we deal with the world in which small volumes need to have access to the highest performance, latest node silicon? And then the third area is an enormously challenging area for us and for the world generally, which is dealing with the threats that we see emerging in hardware security. And here what I really want to emphasize is that we have to deal with an entire range of threats, everything from Trojans to design threats and so forth. But we have to do it not at a single point in the life cycle of electronics, but throughout, such as manufacture, for example, but throughout, everything from design through sustainment. And so that leads to a very broad need to look at security across a wide area. And finally, as I mentioned already, there is a fraction of our office which is devoted to actually building microsystems for specific purposes. Really, those cluster into 4 areas. And those 4 areas are, first, communications, particularly communications associated with things like 5G. This is driven by a need that we see in the military environment, but also in the commercial environment, to ensure that communication links, your cell phone, for example, but communication links of all kinds, are sustained in a continuous way and are ubiquitous, because networking has become important for all domains. The second area is electronic warfare. So by reducing latency in electronic warfare, what I'm really talking about is making decisions faster, having the ability to cognitively understand the environment that you're in and take the appropriate actions. The third area is in generating and directing high-power radiation, lasers, but also more than just lasers. And the last area is a set of technologies that are associated with positioning, navigation, and timing. So understanding where you are and being able to deliver good timing in an environment in which the global positioning service is potentially not available. Okay, so those are the areas that we do broadly, including ERI and also the non-ERI topics. I'd like to spend just a few more minutes talking about how best to engage with us. And this is really focused on those of you who are potentially performers and wish to be performers on DARPA MTO programs. So I think the most important message about DARPA, if I was really going to point at one thing, is presented in this slide. And I would ask people to keep in mind when you deal with DARPA the P in our name. Defense Advanced Research Projects Agency. It's really about projects. So a project is motivated by a specific problem, right? So we are organized to address specific problems. So when you deal with DARPA, it is very important before you talk to a program manager, for example, to think about not just the technology solution that you're going to offer, but to think about what problem you're trying to address. That's exactly what the program manager will be most focused on. And the other key thing, which really subsumes what I just said a second ago, is the Heilmeier catechism. If you're familiar with Heilmeier, he was a former director of DARPA and very famously put together this very, very simple 5-question recipe for designing how one should do research, not just at DARPA actually, but in general. And it certainly was applied and at that time and is still very much used at DARPA to prioritize and make decisions about how we choose which efforts to fund. So it's great to be aware of these 5 questions, this catechism as it's called, but also to have answers to as many of these questions as you can, again, when you're addressing DARPA program managers. So generally speaking, there are 5 ways in which DARPA funds performers, and these are shown here. Probably, without any doubt, the most important way is through large programs. So programs can be of all sizes, sometimes relatively small, a few $1 million, but they can be very large. It says $50 million, but there are certainly many examples of programs that are in excess of that. A typical DARPA program might last about 4 years, again, with a range. But the key thing you want to know is how do you find out about these programs, and that is through what's called a broad agency announcement, or a BAA. They're published, and programs are invariably about solving a specific problem of national security interest. Again, the P in DARPA. So that is the most important thing. And many of the other rows on this chart can be understood in relationship to servicing programs from our perspective. Seedlings, for example. Seedlings are early studies that ideally lead to programs, or at the very least answer questions that a program manager needs to have in order for him or her to define a program. They tend to be much smaller, and it's critically important if you're going to propose a seedling that you understand that the duration needs to be fast and that it ultimately should be connected with a program idea. So if you're interested in a seedling, you should be talking to the program manager not just about that seedling, but what that information will help lead to. There is a particular BAA, often called the office-wide BAA, which is published every year, and this is the vehicle that you use. Responding to that BAA is the vehicle that you use if you're interested in seedlings. But the most important thing, and in general, this is going to be true for everything I'm going to talk about, before you submit a seedling, you should engage directly with the program manager to get a sense of what he or she is interested in. The third area is something you've heard about at the summit already. It's called Microsystems Explorations, MUEs. Those are cross in between. They're not quite programs. They're smaller than that, but they're a little bit more structured than an individual seedling. Typical award is $1 million or less, and typical period of performance, in fact, is always 18 months. And those are organized through what's called a PA, which is another vehicle similar to a BAA. The purpose of MUEs is to do early foundational work to understand new ideas and address new ideas, ultimately with the idea, again, that if successful, these may lead to future larger scale programs. Beyond that, there are two other sort of more specialized ways in which to deal with DARPA, SBIRs and STTRs, like other parts of the federal government. We have available money for those purposes. The rules here are very similar to the rules for any other organization that has SBIRs and STTRs. So you have to meet conditions like, for the case of a small business, for SBIRs, you need to be a small business and meet those qualifications. And you find that generally the rules and the way in which we operate are very similar. However, we're a little more flexible than other organizations in the sense that we compete SBIRs and STTRs year-round. So once again, the key step is to go engage with a program manager in an area that you think might be interested in the topic that you happen to be interested in. And lastly, we have a particular program that's called the Young Faculty Award, which is a way in which we like to recruit younger faculty. It's not limited just to academic organizations. The definition is somewhat broader, but really it amounts to researchers who are early in a field for them to explore specific ideas. And you can find information on that in its own BAA, which is actually administered by our partners in the Defense Sciences Office. So in every case, the key message here is if you are interested in working with DARPA, you want to directly engage with program managers in the areas in which overlap with your technical area. MUEs, I've mentioned already. The key thing is the 90 days, and I think a lot of this we've covered, but I included this just to give you a specific reference to that particular program announcement. And here I've shown a few examples of MUEs that we've done in the last year. So talking to a program manager is where I'm going to end up. How do you know who to talk to is a constant challenge. The best place to begin is to look at our webpage, www.darpa.mil. See if you can find someone from the description whose technical interests appear to overlap with your own. Then contact them. PMs are invariably interested and available for technical discussions and will try and engage with you. But if I may, let me give a couple words of advice. Keep in mind that program managers are really looking for projects. They're looking for programs. They're going to be excited about your latest technical result, certainly, but only if you can put that in the context of how a new program could be inspired or could result from this interesting technology development. And so I think when you present your ideas, you probably want to construct them in a way that appreciates that that's what they're looking for. Program managers are always thinking about the Heilmeier catechism. So as many of those questions that I mentioned before that you have insight to, try and answer those for the program manager and help him or her think through what that means. I like to say that PMs are best when you do their homework for them. So it probably is best to do their homework, or at least as well as you can before you engage them. And finally, it's important to listen to them. Program managers hear a lot of information, a lot of ideas are thrown at them, and they have a lot to process, but they have a lot of insights too. So it's important not just to be on transmit, but also to listen to what the program manager is trying to tell you. So that's sort of a whirlwind view of the office. I wanted to end really with this, the most important slide. I think you have seen this already, but this is the current crop of program managers in MTO. These are exactly the people, the ones in the second and third row, that you want to go talk to about technology areas and hear a few words are said about each program manager, giving you at least an insight into what areas of expertise they are most interested in. And with that, I believe the plan is to spend the rest of the time we have available to answer your questions.
And now, moderating our panel with program managers within the Electronics Resurgence Initiative, DARPA Microsystems Technology Office Deputy Director, Dr. Dev Palmer.
Now we're going to move into a virtual Q&A. And please enter questions in the box right under my picture, and we'll do our best to answer them during the session, which is going to last about 25 minutes. I have a few questions that we didn't get to yesterday just to get things started off. This is mostly an MTO 101 Q&A, but since we are holding this jointly with the ERI Summit, I thought I'd start off with a couple of questions about the relationship between MTO and ERI. So first question is, how does ERI fit into MTO and vice versa? And really, even though we're having two separate events to cover these two activities, they fit in one strategy. MTO has the mission, as Mark told us, to deliver capabilities, microsystem capabilities to the DoD. And you can't do that if you can't build the microsystems. So ERI has helped MTO build closer relationships to the commercial semiconductor industry. And that gives us access to not only more advanced semiconductor technologies in many cases, but also to the broader market support for the technology once it does get developed. And so another question, interesting question that came in was, what areas within ERI and MTO do you think people might overlook but are vitally important to advancing electronics? And I think one of our fellow PMs, Ted Senator, who manages a program in MTO but is seated in DSO, said it best. He said that our job is taking concepts from disbelief to mere doubt. You can kind of think about that in the context of the phrase everybody's heard, what is DARPA hard? The way I see DARPA hard defined is that the idea sounds impossible on the surface, but you can actually put together a logical set of technically defensible steps that could get us from here to there. And ERI has a lot of programs that are doing just that right now, which will pay great benefits to both the systems that MTO, Microsystems MTO is developing and in commercial industry. So I think we had one come in over the wire. Joe, is that one on the way? Thank you. How does DARPA deal with ITAR, EAR, and international performers? Well, that's a very complicated question, as everyone who has dealt with the international, the ITAR and EAR knows fully. So DARPA does not unilaterally determine what technologies are ITAR or EAR. Those are determined by the regulations, the relevant regulations on those two programs. But we do want to work with international performers if that's where we can get the best technology. So certainly we want to protect intellectual property. We want to keep ideas with their originators as much as possible. But I think you can't you can't restrict your collaborations to just people within the U.S. if there are good technologies available elsewhere. We'll follow the regulations to the best of our abilities and do determinations on the technologies that we're funding as their technology readiness level advances. And when it does appear to cross that threshold into a critical technology, then we'll engage with the performers and make sure that we have a plan to make sure that we're following those regulations. Okay, I think that covers that one pretty well. There was another question that came in that's pretty interesting. What is the biggest misconception you find people have about ERI, MTO, and DARPA? And one of the biggest misconceptions I've heard about ERI, both when I was at DARPA, right as ERI was starting up, and then as I transitioned into industry for a couple of years, is people were wondering how a $1.5 billion investment over 5 years could possibly impact a $400 billion a year industry. Well, we're not trying to completely change the industry, of course. We're just trying to develop more of a tie between DARPA, the defense industrial base, and the commercial silicon fabrication industries. And so that investment is actually supporting a lot of collaborations where we get a better understanding of what the commercial industry's directions and needs are, and they also get a better understanding of the kind of high mix, low volume capabilities that the DoD is looking for. And I think it's a great way to take steps towards solving that problem and giving the DoD access to advanced microelectronics. The biggest understanding that I hear about MTO is kind of a misunderstanding on how programs are developed in MTO. I used to tell people that DARPA PMs don't have any money, which is kind of shocking to some people, but it's true. They start out with no budget, effectively. The only way they get a budget is by selling innovative programs. And it's certainly happened, but it's rare that a PM comes into DARPA with a program that's fully baked. It usually requires a lot of interaction with the research community and the potential performer community and the user community to really understand exactly what the problem is that we need to solve and how best to solve it in a way that can be accomplished within the scope of a typical DARPA program. And the biggest misconception I've heard about DARPA is that we're a blue sky research organization. It's true that we try to push the outer edges of the innovation landscape, But as Mark said in the overview, don't forget the P in DARPA stands for projects. So even the most fundamental research projects that we do at DARPA are goal-oriented. And the other misconception about DARPA is that we have some kind of sophisticated science fiction laboratories in the basement. We don't have those at all, despite what they say in the movies, which is why we need to have strong relationships with the research communities in government, industry, and academia. Okay. All right, so the other question that involves both ERI and MTO asks, what is the right balance for ERI and MTO in terms of addressing commercial needs and defense needs? Well, that's going to sound the same as the answer to a question from earlier, and that is that ERI gives MTO access to the high-performance commercial and dual-use technologies that are critical to microsystem dominance, which in turn is critical to MTO being able to deliver capabilities to the Department of Defense. That is our fundamental mission, after all. And the ideal scenario is when we can develop and transition a military technology that also has a commercial adjunct so that the economies of scale can help support both the quality and the cost of the technologies that we need to use in the DoD. Oh, thank you. Okay, this is a great question. What happens if you contact a PM with Heilmeier charts and you get no response? I can tell you that the PMs probably can empathize with that situation because they send Heilmeier charts to the office leadership, and often it takes a while to get a response. I think the best advice I can give you on that is to contact the PM again. What you have to remember is that the limited term of a DARPA program manager forces a very high operational tempo, if you will. They're very busy people. They are trying to start as many programs as they can. They're talking to as many researchers as they can and members of the user community. And but fundamentally, you join DARPA to serve the public, to help change the trajectory of the technology vector for the United States. And you are a public servant. So if you don't get a response from a PM, you should keep contacting them. Make sure your message is crisp. Make sure that you're emphasizing the innovative problem that you're trying to solve. And I know that PMs are going to hate me for saying this, but if you still don't get a response, you can always contact me or Mark, and we'll see if we can help you out. Another great question that came in asks, are universities always subcontractors, or can they lead programs? Well, of course they can lead programs. We have several funding mechanisms that are essentially directed towards universities or early career academics and their equivalents in the nonprofit sector, such as a YFA program. It just depends on the nature of the work. Universities do contribute a large percentage of the innovative ideas that come through in the DARPA programs. But the place where you run into issues when they are subcontractors is if that innovative idea and that technology development is on the critical path for a program, because typically the defense industrial base operates at a kind of a different rhythm than a university. I think in some cases it's useful to have parallel tracks in a program where One is more oriented towards the typical defense industrial base performer with the measurable milestones, and the other is a more university-directed program where they're exploring ideas that can then feed into the other track of the program. That way you maintain some independence over your fate in the program, but you still get to participate, you still get to share ideas, and ultimately that's what it's all about. Thank you. How are the metrics for ERI and other MTO programs determined? Is there any difference between ERI metrics and non-ERI metrics? Fundamentally, there is no difference. The metrics of a program are how you tell whether or not the program has been successful. So typically, what we want to see on a metric is a large advancement over the current state of the art in expanding the capability space for a particular device or component or subsystem that then expands the palette of the system designer to help them explore more options in how they put the systems together that potentially can reduce size, weight, and power and increase performance. It really depends on the problem you're trying to solve, but it's critical to have metrics that determine that you are making progress towards the goal. And it's equally critical to define how you're going to measure the metrics so that everybody's talking about the same thing when they report the results. In terms of the difference between ERI metrics and non-ERI metrics, certainly the nature of the research is different. There are programs in MTO that are not programs in MTO that are not related to ERI for various reasons. And not every program in MTO is reliant on advanced fabrication nodes. So the specific metrics and how they're defined depend on the specific research program. But you're trying to, I'll say it again, the fundamental idea is that you want to know that you're making progress on the program, and you want to know how to measure the metrics so that everyone reports results in the same way. Let me just do that one. So another question came in. I just found out about a DARPA program that's been going on for a while in an area I'm working in. How do I submit a proposal for a grant? Well, unfortunately, if the program has been going on for a while, the source selections have already happened, and it's very likely that the money has been spent. So responding specifically to the idea under that announcement is probably not going to get you anywhere, but you always can put ideas, proposals in through the Open Office BAA. In any case, the most important thing to do is what Mark mentioned in his talk, and that is talk to the program managers before you submit anything, because that's the best way to get aligned with their thinking, get your thinking lined up, and make sure you're solving a problem that they're not already trying to solve, and that's of interest to them. Another one came in that says, what is the difference between a MUI and a seedling? How do you decide? There are several differences. One is that the MUIs and the seedlings are executed through different solicitations. The MUIs have specific research program announcements that come out for the MTO topics. And a seedling typically comes through the Open Office BAA. The other distinction is that MUIs have to be another transaction with payable milestones, and that allows us to execute them very quickly so that we can go from announcing the program to actually executing or awarding the contract within 90 days. The seedlings, on the other hand, are typically grants or more regular cost plus fixed fee R&D contracts, which can take longer, but offer some flexibility that the other transactions don't. There's also a difference in the time that the programs can run and the amount of money that can be invested in each program, and you can find those details in the specific announcements. Thank you. Hi. So there's another question related to seedlings and MUIs. What are the good months to contact a PM for a seedling or a MUI? I would say that your best bet is to contact them between January and December, because we are always looking for good ideas. Certainly, I think the motivation behind this question is the annual DoD budget cycle. So the subtext is when do PMs have money to spend? I'll say again that PMs only have money to spend if they can convince the leadership, often all the way up to our acting director, Peter Heinem, that it's a project worth funding. So if you have a good idea anytime, don't hesitate to bring it to a PM or multiple PMs. Another question here, are DARPA proposals usually from a single organization or from teams? That again is heavily dependent on the problem that we're trying to solve in the specific program that you're talking about. For example, the YFA program that I mentioned earlier is typically a single organization. Large, complicated technical problems that involve everything from fundamental research to technology transition almost have to be from teams, but there's no hard and fast rule. Basically, we're looking for, in a proposal, we're looking for a credible and complete description of how you're going to do the work and who is going to do it. So yeah, it can be either. And I think we got time for just a couple more questions before we wrap it up. Hi. Speaking of YFA, is there anything different when discussing a YFA compared to regular programs? Well, again, I'd refer you to looking at the specific solicitation. A YFA is targeted for academic research, so fundamentally it's going to be different from the large DARPA program BAAs. And I think I'll just leave it at that. You're better off looking at the specifications in the solicitation for any given program. And the last question I'll take today is, where do PMs come from and how long do they stay at DARPA? We'll recruit PMs from anywhere. We have people from industry, academia, other government organizations. DARPA has a very flexible hiring authority so that we can bring in people either on loan from other government organizations and nonprofits or as full federal employees on a term assignment. And typically the first leg of the assignment will be on the order of 2 years, which is probably about as long as it takes a PM to get their first program on the books and up and running. And typically the limit on an assignment is somewhere around 6 years, renewable after the first 2 years on an annual basis. But how long you stay at DARPA pretty much depends on your programs and your relationship with your office leadership, for all you PMs listening out there. So I'd like to wrap it up by thanking everyone for the interesting and insightful questions about MTO and ERI. And I hope that I managed to give some informative answers. And if I fell short on that task, I welcome you contacting me offline, dev.palmer@darpa.mil. So now we're going to go into an early break. And after the break, we're going to bring in more people to answer more questions about MTO. This time, some of our distinguished program managers with the questions focusing on their programs and technologies. And I'd like to remind you that during the break, you can enter questions in the Q&A panel, and we'll collect them and try to get to them during the panel with the program managers. So please enjoy the break and rejoin us at 4 o'clock. And I'll start out by doing some introductions. YK Chen joined DARPA in the fall of 2017 from Bell Labs, where he was a senior director. YK is exploring semiconductor optoelectronic materials, devices, circuits, and advanced system applications at the intersection between AI and communications. Currently, he's managing the Frank and T Music programs under ERI, along with the ERI Defense Applications Program. Next up is Bryan Jacobs, who came to MTO in May of this year from Berberian and Company, where he was an advanced technology consultant. Bryan is working on code development of algorithms and novel hardware architectures for optimization, machine learning, biometric encryption, and sensor processing. And Bryan currently is the PM on the Hive program. Tom Kazior signed on in July, leaving his post as Senior Principal Fellow at Raytheon IDS. Tom's interests include semiconductor device design, fabrication and integration processes, including 3D heterogeneous integration for RF arrays, and microwave, millimeter wave, and submillimeter wave devices for sensors and communications. Gordon Keeler, the senior PM on the panel, came to MTO in August of 2017 from his position as principal member of technical staff at Sandia National Labs. Gordon is focused on development of emerging photonics, electronics, and integration technologies to open new pathways towards revolutionary optical microsystems. He's the PM on the CHIPS, PIPES, and LUMOS programs under ERI. At the other end of the PM lineup, Ali Keshavarzi joined MTO from Stanford University just a week ago Monday. Ali is developing programs in foundational capabilities for compute efficiency improvement, including new device technologies, computing hardware, and information architectures. Ali has taken the helm of the software-defined hardware program. Joining us from cyberspace, Serge Leaf enlisted with MTO in August of 2018 from Mentor, where he was Vice President of New Ventures. Serge's programs encompass computer architecture, simulation, synthesis, semiconductor intellectual property, cyber physical modeling, distributed systems, secure design flows, and supply chain management. And he also is interested in startup ecosystems and the business aspects of technology. Under ERI, Serge is managing RTML, AISS, IDEA, and POSH. Last but not least on the panel, Keith Rebello followed a few months later in October 2018 after his service as Technical Director for Emerging Technologies and Technical Lead for Emerging Threats at the Office of the Undersecretary of Defense for Intelligence. Keith is exploring materials, devices, and architectures for artificial intelligence, space, and cyber operations. He's currently managing the SITH program and the Sheath MUI program. So we'll start out with a few PM-specific questions. And since Ali just joined us a week ago, I thought I'd throw him right into the fire, starting with this question. One of the ways ERI was going to overcome the end of device scaling was the incorporation of new materials and device types into CMOS. What ideas are you thinking about that will achieve this goal?
Thanks, Steve, for the introduction, and I want to also welcome everybody to the panel. Materials has always been important and historically have contributed to the evolutionary progress of the mainstream Moore's law over the years, achieving lower cost transistors and higher density. Materials provided a step function improvement in lowering resistivity, for example, contact resistance, interconnect material, barrier material. Dielectric constant increased in the gate stack of the transistors was directly related to material. And we had also lower dielectric constant material for the inner layer dielectrics in the back end, going in the step improvements. And in transistors, of course, we had source drain and channel and mobility material, and the list goes on and on. One of the interesting areas in the alternative novel materials is in the area of the memory technology as it relates to computing and modern workloads and our future architectures. Perhaps we can combine new materials and new physical phenomena, particularly if there is an interesting physics behind it, for fundamentally disruptive memory compute elements. And I emphasize memory compute elements that have characteristics, for example, such as lower energy profile, reaching to femtojoule per bit, providing higher density, and perhaps multi-bit per cell capability. Particularly if these things are in advanced building node technology nodes, hand in hand with the logic transistors and the SRAM, we can really do we can address some of the challenges of the computing that we are facing. Imagine embedded memory that is dense, is fast, and consumes lower energy and lower power, and works in concert with those elements that I mentioned. Next fundamental innovation that can be based on physics of ferroelectricity that has been around for a century. There is a new development in the past few years that a CMOS compatible material, the hafnium dioxide, which is a gate stack of the advanced transistor nodes, has shown the ferroelectricity. If you can use that thing, then we can integrate this material in the front-end process of a CMOS technology that is hard to be achieved. If we do that, ferroelectricity polarization switching, it only requires an atom to move by an angstrom. So inherently it's low energy compared to the alternative mechanisms of forming a filament, moving atoms over tens of nanometer, or charge, or other mechanisms like magnetism. We talked yesterday on how such fundamental capabilities can bring compute efficiency while delivering performance in data-oriented applications, and for taking compute closer to the data. That was what I refer to as edge intelligence. So with that, Dev, I park it for if there is any other interest later on.
Oh, thank you, Ali. For the next question, we're going to go to the internet and ask Serge. As ERI points out, the cost of designing into advanced nodes can be enormous. What technology developments can help mitigate this cost so that companies and researchers outside of large commercial entities can continue to try to innovate?
Thank you, Dev. Indeed, there have been assertions in the press that it might take as much as $500 million to get a chip project to first working silicon on a 5-nanometer node. It's quite clear that underlying economics would only allow large, well-funded companies to drive deep chip innovation at advanced nodes. The startups will not be able to raise the kind of capital needed to attack these advanced nodes out of the chute. They will likely be forced into incremental strategies, like demonstrating potential of their innovation on older, less expensive nodes, and then on the strength of the demonstrated capability and market size arguments, go to venture capital to find funding to enable the implementation on state-of-the-art nodes. This puts the startups in the US at a substantial disadvantage, and we are actually thinking about a number of strategies for how we can help US chip startups get off the ground in light of this rapidly increasing costs. There are also intermediate approaches that small companies can consider, like perhaps those enabled by the heterogeneous integration platforms, where tiles or chiplets implement accelerators and protocol engines, and they can be combined with commercial and programmable fabric in one package. So platforms like that can demonstrate novel capabilities and potentially unlock the investment that would lead to state-of-the-art manufacturing.
Thank you, Serge. So I'm going to move on to a question for both Tom and Gordon. We'll start with Tom. Both of your bios mention integration and heterogeneous integration, and that can mean different things to different people. So what does it mean to you, and what can we expect to see in this area in the coming year?
Well, I certainly agree with the comment about heterogeneous integration means a lot different things to different people. And I saw that firsthand when I got involved with the IEEE heterogeneous integration roadmap. I went to a meeting there and there was probably 30 or 40 people and there were 30 or 40 different answers to heterogeneous integration. If we go back far enough, I think the heterogeneous integration has been going on for decades, where we build modules, TR modules, multi-chip assemblies with different technologies in them. But that was all called on a macro scale. I'm also interested in pushing that to the micro and the nano scale, where we're doing heterogeneous integration of different materials, different semiconductor materials, different functionalities now kind of within the chip or within the package. And ultimately, if we could take this to its ultimate extreme within the transistor itself, integrating diverse materials to kind of further optimize the performance of the device. It's maybe analogous to what Ali kind of said of looking at the ferroelectric properties of a gate oxide, but can we individually optimize materials in a transistor for different aspects of the transistor to get either better RF transistors or better digital transistors? I mean, ultimately, what I envision in the near term is more looking at kind of called the micro scale, is how do we best integrate compound semiconductors, 3-5 semiconductors with their performance advantages with the high density integration that you can get with silicon CMOS to kind of get the best of both worlds. And that's kind of what I envision, at least one of my initial efforts or programs. But ultimately, long term is kind of going from the micro scale actually down to the nano scale of heterogeneous integration.
Gordon, what's your take?
Yeah, so I actually completely agree with Tom. I think that there's these sort of different layers of heterogeneous integration, where, you know, under chips, it's about putting together different technologies from different foundries. But then when you start adding different functionality like photonics or MEMS, it gives you new kinds of capability. But where it gets super interesting, right, is this sort of wafer scale integration of new materials. And we have some programs already in ERI doing that. And the one that I'm excited about, since we're just kicking it off, is Lumos. It's about bringing new materials, again, 3-5s and other things to the platform. As far as what's coming in the next year, you know, there's several different materials coming to silicon and other platforms in Lumos. What I'm maybe most excited about is optical gain. In particular, some of the 3-5 quantum dot materials look really promising for lasers and amplifiers. They have great properties, and in particular, super defect tolerant. And so you can imagine doing heteroepitaxy of materials right on silicon and still making good lasers. We're also looking at nonlinear materials and non-reciprocal materials. So anyway, I think there's a lot to come, but the exciting part is around new material integration.
Thank you. So heterogeneous integration is a field of great interest these days, as is advanced AI and neural networks. So here's a question for YK. How are advanced AI and neural networks being brought to bear on your programs and your thinking on new program ideas?
Yeah, thank you. I think in the past 5 and 10 years, the AI has been finding a lot of good applications. For example, you use Alicia and the iPhone. But a lot of these AI are being processed in the cloud and data center. And so basically your phone or the IoTs has to relay the data to the remote cloud center. But so in order to get a fast processing, we have ERI program, Frank, try to have some new method of doing the in-memory computation to give you fast results and lower power for the mass computation. But about 2 years ago, when we had the first ERI summit, and Dr. Hava Sigmund and me was supporting an AI workshop, and toward the end, we have the panelists give their opinion. I think people from NVIDIA and Xilinx and other people. So they'll say one thing kind of interesting. They say if we can start over again, and we might not like to pursue the current approach like deep neural network. So the issue is to get a good accuracy, you need a many layers of the deep neural network. Then it consumes a lot of computation power. That's why MTO, we started a few exploratory programs to see how can we bring the AI to the edge. So first thing we have to address is what kind of new architectural algorithm instead of DNN, we can simplify the processing. And second, can we use different kind of data representation rather than the current things and try to use very simple logic operation for computing rather than the typical multiplication and the add and the accumulation, the kind of things that consume a lot of power. So with all those things, then we understand with those programs, there are potential paths to make the AI neural net much simpler and a little bit efficient and high latency. One of the challenging is if we want to bring to the edge, for example, we want to build an AI radio, you have to compete really against the existing radio, which has been exists for about 40, 50 years and very well polished. So how can AI bring extra functionality, still operate at the same form factor and the power, but give you much more intelligence, like conceptual and the learning? And so there are a lot of interesting things we can build. So I think like what Mark said in the previous session, DARPA is exciting to build a new program to change the new paradigm for the warfighter. So I think for me, I would like to bring the AI to the edge, communication and sensing, particularly in the wireless area. So in that case, we can get a new capability for both commercial and the DoD applications.
Thank you, YK. Let's go to Bryan for the next question. Is there ERI MTO work on advanced algorithm development? How do the algorithms fit into the advancement of the underlying hardware? And can we expect to see programs addressing algorithm development?
Hey, Dev, thanks. That's a great question because a lot of people might not necessarily associate algorithm development with microtechnology development. And if we're talking strictly about algorithms, that might be true. However, as we move forward and we look at advanced architectures for solving problems and more specialized problems, we quickly realize that our old metrics like gigaflops per watt are no longer appropriate because that is somewhat irrelevant in terms of the ability to solve the problem at hand. So for example, my program Hive, the metrics are more like traversed edges per second or per watt. And I think as we see the architecture specialization for specific problem classes grow and continue to grow, we'll see more of an effort into the surrounding algorithms to take maximal advantage of that. Now, some people might say, okay, well, that particular example, it's a little bit of a magic to match an existing graph algorithm into that architecture. And that might be a valid point of view. However, as we try to go further and embed more unique and different varied phenomena into a digital architecture, like for example, coupled analog oscillators or systems that don't fit the traditional paradigm, we then quickly realize that one, we don't even necessarily know how to quote program them anymore. And so we have to, in some cases, come up with whole new paradigms in order to operate the underlying electronics in a manner that we get the result back that we're looking for. And so the metrics that I see us evolving to are not flops per watt, not traversed edges per watt, but something more like solutions per joule for many of these types of architectures. And so as soon as you realize that such a high level metric, the way in which you operate the hardware and the underlying algorithm become tremendously important. So I think that this will increase going forward in the future as we get more diverse about how we're actually, what we're actually embedding in our architectures. Thank you.
Keith, it seems like in past efforts in hardware security, the security comes in after the hardware is designed. How do you design in security and keep it from becoming very expensive and very quickly obsolete?
Dev, you're absolutely correct. Oftentimes for DoD products or even commercial products, we are laser focused on performance and power, and security is kind of bolted on in the back end at the last minute, and that has that's costly, not just in terms of money and dollars, but also it limits our ability to protect ourselves from cyber attacks. At DARPA, we're pursuing approaches on both SITH and the ACE program that make security an intimate part of our designs. On SITH, we are developing security architectures that minimize the impacts on power, on area, on performance. And ACE is looking at incorporating these advances and allowing us to optimize our designs for security, for power, for area, for performance. And so what we're really trying to do, I'm gonna steal a line from Serge, who's up in the cloud. We're really trying to make security ubiquitous and sprinkle it into everything that we do, much like fluoride is in our water, right? So by doing this, we believe that we can really reduce the cost of security going forward. The other point, on obsolescence is very important to us in the DoD in particular as well. We don't have the volumes that the commercial manufacturers have. So oftentimes we don't have the opportunity to make multiple spins of our ICs. And so being able to have techniques and technologies that allow us to fix bugs, that allow us to update our security protections is very important. And that's, some of the technologies that we're developing on SITH are aimed at solving that problem. We want to be able to recover and anticipate. We can't anticipate every type of cyber attack that might occur. So we need to be able to adapt and adjust our architectures to evolve over time without having to respin them.
I'd like to add a little bit to what Keith, this is Serge. I'd like to add a little bit to what Keith had said, and that is in ACE, we incorporate security right into the fabric of the chip design. And to address the question that Dev posed about forward-looking support for newly emerging threats, what we have in ACE is an on-chip security engine that is upgradable with security policy throughout the life of the host device. And so we hope that the attack vectors we did not anticipate at the construction of the chip will be able to deal with them through those updates.
Thank you, Serge. Don't get off the line yet. We're about halfway through the Q&A session, so we're going to move from the individual questions out to panel questions. And Serge, you have extensive experience in the commercial industry. The question is, for those who on the panel with commercial or defense industry backgrounds, what have you learned since you've been at DARPA that you wish you knew before? So Serge, would you like to start?
Yeah, what I learned is that this really is a unique opportunity to take a vision that you have and get it realized. So when I was in commercial industry, I saw numerous opportunities for innovation, but in the corporate environment, I could not get those things funded because of business model issues, market size issues. And despite the fact that the things that I was looking at were profound and revolutionary in many cases, the funding mechanics in commercial world were not supportive of investing in truly big ideas. So what I found is that the power of DARPA is that you can express, the challenge is you have to express and articulate your vision and describe the problem that you're trying to solve, but stop short of articulating the solution. And what I found incredibly rewarding and empowering is being able to focus some of the best minds in the world on things that are really important for both national security and economic competitiveness. So this is my recruiting pitch to the potential PMs. This really is a wild ride, a career-defining experience, and it's like living on a dog time. Every day at DARPA is like 7 days in the real world. And so, but everybody, all the PMs know the clock is ticking. And so you have very limited amount of time to advance your vision. And my motivation is really pure here. I just want to move the needle on science and technology in the areas that I have observed requiring attention when I was in the commercial world.
Thank you. Anyone else on the panel want to take a shot at that one? Tom?
Yeah, since I spent my entire career working at a defense prime, I actually worked on a lot of DARPA programs as an individual contributor or a PI. So I kind of had a good idea what it was working with DARPA and DARPA programs from a performer side. Now that I'm on the other side of the fence, I get a complete different perspective, and there's just such a whole wealth of ideas out there of people who want to share ideas with you to help solve problems, help formulate what the challenges are and what the problems are. And again, as Serge pointed out, to help develop the technologies to kind of move the needle, and from my perspective, to help improve situational awareness for the warfighter and kind of make a difference. Instead of just having resources of all the company that I worked with available, now I have resources from the entire country available to help attack some of these problems. And I hope to use that as I look at heterogeneous integration at the micro and nanoscale moving forward.
Great. I want to move off of that question for a minute because we've had several follow-up questions come in over the wire. One for Keith. How do you measure hardware security?
Well, that is very challenging, right? So there's no real good way. I think we heard this morning that the CEO of ARM mentioned there's no real way to do that. And that's one of the challenges that we've undertaken on the SIF program is that, on SIF, we're developing these secure processors, but how do we know if they're doing their job, right? So we've developed a tool to do software security benchmarks. So we are evaluating all of the architectures on the common weakness enumeration and common vulnerabilities that MITRE and NIST have developed and published. So there's a large database online, and we have a software tool that generates, much like synthetic software benchmarking, it generates synthetic security benchmarking programs that run on the architectures, and then we can use those to evaluate the performance of our systems.
I'd like to add
Thank you, Keith.
if possible, this is Serge. So it's a great question because security by itself is a vague thing. It cannot really be measured. So what we have to do with ACE is we have to define security in terms of attack surfaces that we wanted to defend. And then we divided those attack surfaces into supply chain attacks, side channel attacks, reverse engineering, and malicious hardware. And when you narrow the focus or narrow the definition of the attack surface, it becomes possible to measure resistivity of the defense mechanisms and countermeasures on those at the level of a particular surface. It's harder on some than the others, but ACE program, which a lot of it is available, information is available online, actually articulates some metrics related to hardware security.
Oh, thank you, Serge. And then a follow-up question for Ali and YK. I'll get back to you in a second, Gordon. I haven't forgotten about you. A challenge to new devices such as memory is the reluctance of major foundries to adopt them at sub 10 nanometer nodes. What's your strategy for overcoming that?
Yeah, it's very good question. Certainly from the new technology material from the laboratory into the production, that's a relative long development cycle. So if we look at memory technology, basically a lot of main fabs like TSMC, Samsung, they are really buying the equipment, and today's semiconductor industry, all these recipes go with each equipment. So basically I say I need a new memory deposition system. I just order from Applied Material or other company, then they come with the recipe. So it's like buying the laundry machine. You just put it in the pipeline of your fab. So what we are doing in the ERI is on some of these new memory devices, we work with equipment maker like Applied Material. So when they were developed into original research devices, then kind of sort through all the problems in the production environment, then they will work with the major fab like Intel, TSMC, or Samsung. Then they will be interested to buy those machines. So that's one way to do that. So a lot of the time we don't see that, but it is certain development cycle to get the big end user to use it.
To add to what YK mentioned, also one other alternative is to make sure that the alternative material that you're working on is completely compatible with the tool set that is available. And an example of what I mentioned is the hafnium dioxide tool set. So the recipe needs to change, but the tool can be modularized to service that. I think that's very important. Another thing is we are really not talking about memory for the sake of memory. We are trying to talk about memory that does computing. So that by itself is going to grab the attention because it's bringing value to the systems. It's going to give you better efficiency and higher density of computing. So I think that push and pull combined can provide a chance for the foundries to see the light at the end of the tunnel and develop this material to full maturization later on.
Thank you. Gordon, you mentioned larger scale 3D HI on the wafer scale. As you move to that scale, are there security and trust considerations on your programs? And if so, how would you address those?
Yeah, so good question. I would say that a lot of the HI programs that we're working right now are pretty fundamental in the sense that they're looking to bring to fill gaps in technical capability, and so often, I guess this is going back to what Keith pointed out. The security comes as an afterthought or it comes later. Some of the new materials, though, are pretty good at doing some security kinds of capabilities as well. Sort of puffs and other things come to mind where we might be able to include those as part of our security solution. So, I think it's not a straightforward answer here. I think when you're looking at just developing the technology from the get-go, HI is not so much about security, but if we leverage what we know, I think we can get there.
Great. So I'll throw out a couple more questions to the panel here. Feel free to weigh in. How does the tech review process work? And why does it take more than 3 months from a BAA response to a contract notification?
I hope you're not asking that questions from me.
No, you'll find out. I guarantee it.
Well, I mean, I can weigh in on this, Dev. I think when I came in, I really didn't expect the rigor of the review process that we have to go through. So we have to draw in other experts from the government to take a look at the proposals. There is a very rigid set of steps that we have to go through, and at least in my case, frequently I get proposals that maybe are on the edges of my domain of expertise, and then I have to bring in world-scale subject matter experts to help me assess the claims that the proposer is making. And fortunately, a lot of them are at DARPA, and a lot of my colleagues at MTO are awesome experts in their respective fields, so it's not that hard. But the process is rigid. We are spending taxpayers' money, and we have to do so responsibly, and we have to follow the procedure. We do have processes that are faster, like MUI that were mentioned earlier, that are streamlined in a different way. But as frustrating as it was to me coming in from outside the government, I now feel like the rigor is completely justified.
Yeah, I'll jump in a little bit and say this, Gordon. Yeah, there is a ton of rigor. The way that we evaluate these proposals is actually eye-opening once you're in DARPA, just the number of experts that look at this, the amount of time that everybody spends on the proposals. Now, we realize that often a good proposal can take a performer hundreds of hours to put together, right? And then maybe we get dozens of those to a program call. And our work starts probably a couple of weeks after those get submitted because they have to go through some checks. And so to be fair to all the proposers, really, it takes that kind of time. I'm really happy with how the process generally goes. The worst part is having to narrow it down to just a few when you've got so many good ideas coming in.
Any other comments on that one? Okay, so we're kind of coming down to the end of the session here, and I thought it would be interesting, since we have such a variety of experience levels in the PMs in the room, to ask this question. What is a typical day for a DARPA PM? And I'd actually like to hear several responses on that, if I could. Who wants to begin?
This is Bryan. I'll go first. So I started during COVID, so I don't think I've had a typical day. But even pre-COVID, I worked very closely with DARPA for a number of years in many different roles, as a performer in the past, as a CETA in the near past. And I think the bottom line is you're going to come in and solve a number of problems that get a lot of good work going. It's just not necessarily the one that you thought you were going to solve that day. It's always very challenging and always very rewarding.
Yeah, Dev, I'd like to Serge. So I would say that the new PMs, they don't really know yet what a typical day looks like because they're in the early stages. But I would say that if you're an active PM, you have numerous programs that are ongoing. So you spend some of your time on reviewing progress of your performers, making course adjustments if necessary. I personally do a lot of community outreach for all the new program concepts that I'm developing. I'm socializing them with the experts in the universities and commercial world, both trying to get their perspectives and learn something, but at the same time, trying to get them interested in what I'm doing so that they would consider being proposers. And then a lot of my time goes, those approaches that come through DARPA website, I read them all. And in some cases, they're ridiculous. In some cases, they're just outside of my domain of interest, in which case I try to forward them to other PMs. And in some cases, there is an interesting tidbit, and we decide to follow this up with my team. I would liken the work that PM does a little bit to that of a studio executive, where they hear 12 movie ideas per day, but they can only pull the trigger on funding maybe 2 motion pictures. So something similar here. And so what I've been encouraging all the people that approach is to condense their ideas into 25 words or less, so that I can make a quick judgment if I can afford the time to go deeper. And it's very hard, particularly for the academics, to express themselves in such a concise way. But that's the only way for PM to maintain effectiveness and sanity.
Spoken as a true former executive in the private sector. Keith, you were going to add something there, I think.
So what I hear is that we should start a DARPA tweet proposal submission, idea submission activity here. I was just going to say that I would throw out the word typical. It's been my experience that every day is different. There's some common trends. Meetings, there are a lot of meetings. So, as a DARPA PM, you're managing multiple programs. And so you got to check in with performers, make sure things are going, as planned. As Serge said, we are also responsible for coming up with new ideas and new programs. So you end up talking to, a lot of people about new ideas and things of that nature. We get a lot of phone calls, we get a lot of email. So a significant portion of my day is spent sifting through email and reacting. Thinking. I try and, spend at least some part of the day thinking about new ideas and working on new starts.
Gordon?
Yeah, I'll just add a couple of things. I agree that there's no typical, but it is a great job. There's some stuff that's fantastic, and probably everybody has different favorite parts. Some of those are the new starts, thinking about new ideas and running them down. You have to go really deep into the technical side. Working with fantastic performers and going out and visiting and actually seeing, like on the ground, the real things that are happening. And then one thing that I guess I didn't appreciate until I got here, how important it is, it's spending time working on transition. And so you spend a lot of time talking to transition partners and talking about the success out of your program to make sure that it lives on after just a DARPA investment. So we're not just doing R&D to try and show that something can be done. We want it to go somewhere, right? And so a lot of our job is that too.
Anyone else want to weigh in? Tom?
I was just going to say, in the almost just under 2 months that I've been here, I kind of agree with everything I'm hearing because I'm seeing it firsthand. There is no such thing as a typical day. I'm getting to meet a lot of new friends across industry who want to share their ideas. And once they find out what I'm interested in, some of them are related or linked. Some of them are completely tangent, but you got to have to sift through all that. And there's a lot of good ideas out there which help form or helping shape what I'm going to put out as new programs.
Well, so we're about out of time. One question just came in that I think is important to answer, and I'm just going to answer it very quickly. The question is, how can someone determine which CETAs are assigned to support specific DARPA PMs? And I think that is a great question because it points out that how important CETA teams are to the success of a DARPA PM. And the best way to find out is to ask the PM. So we've had a lot of discussions in this panel, in this Q&A, about people and ideas and what it's like to be a DARPA program manager. So I will wind up by saying that if you would like to consider being a DARPA program manager, please do contact us with your ideas. What we're looking for is innovation. I think your resume may be somewhat less important than the quality and impact of your idea. So if you do have anything in that realm, please come to talk to us. So just to wrap it up, I would like to thank our panelists today. And I would also like to thank the members of the audience that sent in questions. So on the schedule, this is the last event of the day, but before we adjourn, I would like to bring my friend, colleague, and boss, Dr. Rosker, to the podium for some closing comments. Mark?
Thanks, Deb. Well, as you just said, this is the last event of the day that we have scheduled. And so, in effect, this is the last opportunity that we have to say anything to you. So I wanted to say just a few words sort of at the very end of this summit. Planning for the ERI Summit is an ongoing event, it seems like, around here. Many of the people involved were the CETAs that Dev just talked about. We began planning for the summit shortly after the last one, late last year. And in fact, we had selected a site. We planned out a fantastic event, multiple sites actually in Seattle, which would have gone great. But as with so many other meetings and so many other events in the pandemic world that we're living in, COVID-19 changed our plans, and it created enormous challenges for us about having this summit. But I think it's a testimony to the people involved that we regrouped, we planned, we replanned, and in DARPA fashion, we came up with this event. We thought it was very important at a time when microelectronics really has captured the imagination and the attention of so many people, that we have the summit and that we have the discussions that we've been having for the last 3 days. And so we wanted to continue. But we wanted to do it in a way that was as similar to the experience that you would have had in Seattle had we been there, and something that we would be proud of. And we hope that this virtual event has met those expectations and that goal. We think it has, but we hope you, the attendees, have come to the same conclusion. So more or less in closing, I just wanted to express some thanks. As I said, it was a group effort from the team at DARPA, an incredible number of people, but there are a few people I just want to shout out and call out for their efforts. So let me start with the esteemed speakers that we had, the plenary speakers, many very impressive names, and also the workshop speakers as well. So a lot of important leaders in industry and academia and government who took the time to come and visit and spend some of their time with us. The performers at DARPA, everything is possible, but only because of the performers who actually go off and do the hard work. And many were represented, and we thank them for their time and their effort. The PMs, the people in this room, and also their CETA staffs who were involved and worked very hard over the last several months preparing. And I guess I should not forget also our bosses, Dr. Peter Heinem and the DARPA Deputy Director, Dave Honey, who encouraged us and really pushed us to go forward with this event. But at the end, there are a few people who I especially wanted to call out by name who worked many, many long hours. I will not be able to list them all, but here are a few of the names that I really didn't want to forget to say. I'll start with Richard Dwayne Chambers, who you got to meet this morning, who is absolutely instrumental, not just with this event, but with the ERI in general. Monica Barrera, Jackie Wisniewski, Megan Lahr, Alex Moseson, Scott Albus, Jasmine Mack, Joe Maurer, Aaron Martinez, Tom Shortridge, many other people, some of them in the room with me and some of them elsewhere. So I want to thank them all personally for their long hours and hard work. And so lastly, I want to thank you, everyone who has participated. If you have comments about this event, if you have comments about how we're doing in ERI, if you have ideas about what we should be doing next in ERI, please spend a few minutes contacting us, let us know, and share those thoughts with us. And we hope to see you again next year, maybe, I hope, in person. Thank you.